Welcome to this session. Today I am going to discuss about SIMD and SIMT concept, and I will cover the threads organization and its mapping on NVIDIA GPU. I will also discuss about the thread scheduling levels and pipelining that are available in NVIDIA GPU. At last, I will cover how the pipelining structures helps in latency hiding and improving the overall throughput of the device. So, let us start with the first topic of the day, that is SIMD versus SIMT. So, I think so far you have an idea about what is SIMD, single instruction multiple data, and SIMT as well, single instruction multiple thread. So, let us discuss these two concepts in detail one by one, how these concepts are implemented in various architecture. So, let us consider I have a two array 1 and array 2, you can see here array 1 and array 2 is here, and it has some number of elements, and I want to perform that these elements to be added. In generic, I am considering some pipelining structure that is available. So, first unit in a pipeline is load, and second unit is a execution unit where it will perform addition or multiplication, and last unit in a pipeline stage is store unit. And at this side you can see this is a implementation of exact core unit, where you can see there is a load unit which always try to get the data from the global memory and load it to these registers R1 and R2, and each register is of 64 bit. So, these days you know that every machine is almost 64 bit. This data will be go to the 64 bit ALU unit. So, where the actual execution will be performed like addition or multiplication or any logical operation. After this operation, data will be stored in some registers R3 or any temporary registers, and then finally, the store unit will come into the action and will store the result in to the global memory. So, in this scenario I am considering my each element is of 64 bit and it supports double precision. So, let us see how this operation is performed. So, this T0, T1 and T2 and so on, these numbers are representing the clock cycles, and how these clock cycles, what actually happen in these each clock cycles we will see in a step by step manner. At clock cycle T0 in a pipelining stage also you can see that at T0 element 21 and 12 will go to the load operation, or you can say it is a load unit, and it operation will be performed data from global memory to register. So, these elements are loading from global memory to registers. Here you can see this operation where it is happening, a load unit is being performed this operation. In next clock cycle, I am considering these two elements 12 and 32, these two elements is go to the load unit, because load unit is free at that particular time, and the previously loaded data 21 and 12 that has gone for the execution unit. And similarly, in T2 cycle So, you can say that these two elements 4 and 14 will go to the load unit to perform the load operation, you can see here, and just previously loaded elements at A1 and B1 will go for the execution unit. At same time, at same cycle at T2, you can see that the first element that is processed by the load unit at T0 cycle, that has come to the end. So, that means I can say at the end of T2 cycle you will get your first result. So, what the result you are going to get here? So, here you will get 33. Similarly, in next cycle you will get these two elements. So, you can say that it is a 4 and 4. So, these two elements will be complete its operation, and in next clock cycle you can say that it will be next element, it will perform its AND addition operation. So, what is the important point to note here is the register size is of 64 bit and each element is of 64 bit. So, that means, so all elements which are stored in array is each element is of 64 bit. Let us see the next architecture. So, you can see that the execution unit is same, stages is also same, load, execute and store, but there is only one change, that is the register size. So, register size is 128 bit instead of 64 bit, as you can see in a previous case. Here it was only 64 bit, but in next scenario this is 128 bit. So, that means this vector size has a capability to carry or store two elements at a time. So, at T0 cycle, two elements of vector of array A 21 and 12 and of array B 12 and 32 will be processed in one clock cycle. Here you can see that in T0 cycle two elements A0 and A1, B0 and B1 are processed. Similarly, you can see that at the T1 cycle, means next clock cycle, these two elements will go to the execution unit and next two elements of the arrays will come for the load operation. And same thing will happen at T3 cycle. At T3 cycle, or you can say T2 cycle here as per my nomenclature, you can see that two elements will produce the output at T2 cycle. Here you can see output will be 33 and 44 you are getting. So, in previous case in each cycle only one element was being processed, and finally at T2 cycle I am getting the output of one element, because I have increased the register size, as well as you can see that my ALU unit is also supporting 128 bit. Because of that I am able to process two elements of 64 bit at a time. So, basically it is improving my throughput. Let us see the next scenario. In next scenario, or you can say in this scenario, my vector register size is become 256 bits. That means it can carry 4 elements of 64 bit at a time, and my ALU size is also become 256 bit. So, in T0 clock cycle Now, it has the ability to process 4 elements at a time, and I am not changing the pipelining structure. Pipelining structure is almost same, which we have studied for previous 2 cases. It has a load, execution and store unit, but only difference is that because the vector registers has been added and it has a capability to carry more information. So, because of that, each operation has a capability to carry or process more elements at a time. So, in this scenario, it at T0 cycle 4 elements can be processed. T1 cycle, next 4 elements will come into the for load unit to load from the global memory to vector register. At same time, the previous 4 element go for the processing, means addition operation. And similarly, at T2 cycle you can see that I will get my first output here. So, here you can see that at T2 cycle, I have mentioned T3, it should be T2. At T2 cycle, what I will get? I will get here 33, I will get 44, I will get here 18 and I will get here around 108. So, that means in a 1 clock cycle, at the end you can see the 4 elements are being processed. Instead of 64 bit, only 1 element was being processed. So, that is increasing the throughput. That is the capability of vector units. Let us see the another scenario, another organization of the compute units. Here, if you see carefully, you can see that there are 4 units, or you can say 4 execution unit. This is a first execution unit, is a second execution unit, it is a third execution unit and it is a fourth execution unit. And each execution unit has a capability to process 64 bit data, you can see here. And each has a 64 bit register. Each unit has the same set of registers R1 and R2. A vector unit, or you can say execution unit 2 also has R1 and R2. So, means same set of registers is available with each execution units, and each execution unit can process each element independently. So, you can say that the entire array has been divided among these 4 execution units and they are processing. So, in another way, if I look at into, it gives some kind of flexibility. Suppose I have this kind of architecture implemented in my computing device. I have a 4 execution units and I have a freedom to use any of it. Suppose I wanted to process the same vector unit by only 2 execution units, so it can be done. That means, and both the vectors will be divided among these 2. Suppose I have a vector size of 100, then 50 elements will come across here and 50 elements will come to this execution unit. Next, if I have a same 100 elements and I say that this 100 elements must be processed by the all existing 4 execution units, then all 4 units will come into the action and elements will be divided 25, 25, 25 elements and 25 elements across the 4 execution units. And this all execution units are working independently. and these elements will be processed by each independent threads in each cases. These all are processed by independent threads T. So, that means the programmer has a flexibility how many threads he wants to launch, how many resources he want to use, that kind of flexibility it can provide, and developer can use respective programming models that is provided by the device manufacturer or vendor to understand this about how to launch the threads or how to utilize the underlying resources at its capability. So, just we do the comparison here SIMT. So, single thread multiple data versus single instruction multiple data. So, SIMT is single instruction multiple thread and second one is single instruction multiple data. So, you can consider it like when I am talking about single instruction multiple thread, suppose you have an array of 4 elements is 21, 22, 23 and 24, you have to add 4, 5, 6 and 7. So, there are 4 threads, this is a one thread, this is a second thread, this is a fourth thread and this is a fifth thread. So, that is the reason the operation is same, every thread is performing the same operation, suppose it is addition operation on each element independently. So, that is the reason I can say that it is a single instruction because operation is same. So, that is a single instruction, it has a multiple threads. Now, just think for the SIMD. I have again the same elements, suppose 25, 24, 26 and 27 and I want to perform addition of 2, 3, 4 and 5. Operation is addition among these each elements, but all elements are being processed by single thread. Because it has a capability of vector registers. So, all 4 elements can be processed by single thread, but operation, if you look at the operation point of view, you find that each element of the arrays are performing the addition operations. So, instruction is again addition, operation is being performed on multiple data. So, that is the reason we call it single instruction multiple thread, but it will be launched as a single thread. So, just take these two terms, it is clear. SIMT, take the both SIMT and SIMD take the advantage of data level parallelism you have just seen. SIMT can be considered as a constraint form of multi-threading, yes, but SIMD is a constraint form of vector processing. In case of SIMT, many threads each with their own state operate on a scalar register with their own local memory. In case of SIMD, only one thread operates on the vector register, as you can see in this scenario. So, I hope that this concept of SIMT and SIMD you have understood with respective diagrams. Now, let us discuss the organization of threads in Cuda. Just focus on this figure. This part is a software entity and this part you can say that it is a hardware entity. It is a single thread and this single thread is mapped on the single compute core or compute unit. They are basically called by different names, scalar processor, single processor, core, Cuda core, etc. But NVIDIA call it streaming processor. So, each thread has to be mapped on the scalar processor, or in another word we can say that each thread is executed by the scalar processor that is present in the streaming multiprocessor that we have seen in a architecture when we have discussed about NVIDIA GPU's architecture in detail. Next one is, you can see this is a thread block. Thread block is nothing but a group of threads, or you can say the arrangement of threads in a block, and this thread block has a number of threads, and this thread block basically mapped on the SM. So, you know that SM is a streaming multiprocessor, or in another word you can say that streaming multiprocessor consists of multiple streaming processors. Each processor can process, or each streaming processor can process only one thread at a time. So, you can see that threads are mapped onto the streaming processor. Thread block is mapped onto the streaming multiprocessor. And next, you know that each GPU has a multiple streaming multiprocessors. If you remember what we have discussed, that V100 card has 80 SMs and A100 card we have discussed that 108 SMs. To engage all these SMs, you can see in this GPU device has so many of SMs I have shown here. So, suppose you are considering the V100 card. So, this is a SM0 and this is going to be SM number 79. So, basically if you want to utilize all the SMs that are present in the GPU, you must have a large number of blocks. You have to make a group of blocks. This blocks is known as thread blocks, because this block consists of large number of threads. In Cuda programming model, we call it grid. So, the grid is a arrangement of blocks and thread block is a arrangement of threads, and this grid is to be mapped on the underlying GPU to utilize the GPU at its full capability. I think you are aware of what is the meaning of full capability, because we have learned how to calculate the GPU's capability in terms of flops, teraflop, gigaflop, etc. So, there are few points which we have to remember. So, threads are executed by the streaming processors as discussed. Thread blocks are executed by the streaming multiprocessors. Thread block cannot migrate. Once the thread block is assigned to one SM, so they cannot migrate to another SM. Several concurrent threads can reside on a single multiprocessor. Suppose the scenario, I have a 80 SMs as per this diagram, I am consider V100, and I have launched the grid which has 160 threads block, That means each SM must process at least 2 thread block. So, that is the reason we can say that The several concurrent blocks can reside on multiple streaming processor, and it is limited by multiprocessor resources based on their shared memory size, the supported register files, and register files may be huge, but it is also supported it must supported by the algorithm, whether algorithm can fit its data in a register file during the execution or not, that is also the important criteria. So, let us discuss this topic. The kernel executes as a grid of blocks and blocks of threads, as I just discussed. So, at very higher level there are grids, it is mapped on the GPU. Grid is nothing but a group of blocks. Next one is block, this is mapped on SM. Block is nothing but a group of threads. Threads are mapped on SP, you can say it streaming processor. Thread is a software entity that is executed by the streaming processors or scalar processor, you can say. So, I hope that you have a understanding that how the threads are arranged in a programming model, grids, block and thread. So, in this next section I will discuss how to identify the global thread IDs, what are the dimensions of grids and blocks, etc. How to calculate the global block ID and global thread ID, why it is important to calculate in 1 dimension, 2 dimension and 3 dimension, etc. Thank you.